Hello to everyone, I'm Riccardo Molteni, and in this talk I will discuss about quantum reservoir computing and its implementation on gate model quantum computer. So first of all, let me show you two examples in which quantum reservoir computing has recently been applied to, in order to introduce you the kind of task we are dealing with. The first is in the financial world. So we are given the sequence values of the Standard & Poor's index, and the objective is to predict with these values the volatility index in the following times. The second example of application regards quantum tomography. So we are given an input of sequence of beta states of quantum state, and we are trying to learn a quantum map F, which is a linear combination of quantum channel. And the important thing here is that the output for the quantum state at the time n can depend also on the input we are given at time before. So what does these two tasks have in common is the fact that for both we are trying to emulate a nonlinear dynamical map, which means that the output of this map can depend not only on the input at that time we are trying to predict the output, but also at time before. For this reason, we cannot use a feed-forward neural network as the one Sebastiano showed before, because this kind of network processes the input data separately, so it does not matter the order we are giving the input to the network. Instead, we have to use a recurrent neural network, which thanks to the cycles between the nodes of the network, it creates an internal state which can retain information about past inputs. Specifically, we are dealing with echo-state network, which is let's say, a subfield of a recurrent neural network. And the key feature here is that the only parameters which are trained during the learning process are the output weights, whereas the connection between the internal state of the recurrent neural network are kept fixed during the learning process, and moreover they can be chosen randomly, provided they satisfy an echo-state property for which the maximum singular value of the weight matrix W has to be close to 1. Now what we are trying to do is to make a quantum version of this. So the idea is to use an n-qubit system as the reservoir for the network. Why we want to do this? Because we can exploit the high dimensionality of the Hilbert space associated to an n-qubit system to create a reservoir with a large number of nodes. How are we going to do this? Well, we can describe the quantum system of n-qubit with its density matrix, and it can be written as expansion of the basis element Bi, which are the tensor product of the 4 operator of Pauli operator acting on each qubits, and the coefficient of this expansion are the values we read on the nodes of the reservoir. So we can collect this coefficient in an array, and of course it will have 4 to the n entries, this array, for a n-qubit system. One of them is fixed for normalization, so at the end we have that from an n-qubit system we end up with a reservoir of 4 to the n minus 1 nodes. As an example, let's take a look to a reservoir of 5 qubits, which is the one we will use in our implementation. In this case, we consider as the basis operator Bi from I, which goes to 1 to 5, the identity operator acting on each qubit, but the index I, for which we will act with a zeta operator. We call this the nodes associated to these 5 basis elements true nodes, as these are the only nodes we are going to measure during the output extraction process. But through this node, we can control the exponential hidden nodes of the network. And we measure these nodes by simply taking the expectation value of the zeta operator on each of the 5 qubits. So how we can control the hidden nodes from the true nodes is by evolving the system with an evolution. Of course, it acts on the density matrix with a unitary operator U. It acts on a density matrix by conjugation, and on the internal state X, which we defined in the slide before, it will act as a matrix multiplication. If now, however, compare the evolution equation for the internal state X of the quantum reservoir with the one which is usually used in a classical recurrent neural network, we notice that in the latter case, the evolution is not linear with respect to the input values because of the presence of the f nonlinear function, which is the activation function. To recover this nonlinearity in the quantum case, we have to evolve the reservoir with a suitable unitary operator U. So basically, as we said, we take the output from the reservoir by measuring the zeta operator, but this operator can be transformed by conjugation with a unitary operator in a linear combination of the basis element Bi we defined before, so in a linear combination of the value of the hidden nodes. As an example, let's consider as a unitary as evolution operator a C0. Let's consider to inject the input into the reservoir as shown here in the slide. And if now we take, after having evolved the system with the C0, the zeta, the measurement of the zeta operator on the second qubit, what we are going to obtain is the correlated operator zeta 1 and zeta 2, and then it will deliver an output which is not linear with respect to the two input values. Now, so the objective in quantum reservoir computing is to create an evolution for the reservoir which gives to the network a non-linearity with respect to the input values and provide the network with an adequate memory. In the literature, there are a class of maps which satisfy this kind of requirement. They act on the density matrix of the reservoir with the equation with the first equation here in the slide. In particular, where T0 and T1 are two completely positive trace preserving map, whereas epsilon is a scalar between 0 and 1, and this will be the object of our investigation, whereas sigma is fixed but density, but an arbitrary but fixed density state. Now we can transfer this evolution equation, which acts on a density matrix, on a circuitous quantum computer, which deals with pure state by an ensemble description. So basically, we prepare an ensemble of quantum states, which are quantum circuit, and evolve them by the probability law, or the input-dependent probability law, which is here in the slide. So basically, we evolve the system, we reset the system with probability epsilon to the whole spin-up state. Otherwise, we will evolve the system with operator U0 or U1, depending on the input values at that time. So the outline of the entire algorithm consists in two parts. A quantum part where we inject the input value into the reservoir, we evolve the reservoir with the quantum evolution, and then we we measure each qubit of the reservoir to take the output, to extract the output, and of course, if we have L input times L input array, we will end up with a L by 5 matrix X. 5 is the number of qubits of the reservoir. We train a subset of this data to get the optimal output weights, and finally we test our results by comparing the output from the reservoir with the one expected theoretically from the task. So in our implementation we use 3 kinds of tasks. For all of them, the input was an array of L values, randomly sampled between 0 and 1. The target output that we want to learn, the reservoir to learn, is an array, again, of L values, which depends on the map of the task. For task 1 and 2, we employ second order degree map. For task 3, instead, we use a pair of differential equations and take as a target the first coordinate. So we first run our experiment on the simulation machine. So basically, the IBM Qiskit simulator. We use an input array of 60 values trained on the first 45 of them, and the last 15 are simply, we simply compare the output from the reservoir with the one theoretically expected from the task. We repeat the experiment for different values of the epsilon, and here we show the results for epsilon 0.5 for the free task. Below, instead, we show the error, the average error for each epsilon for the free task. Now we can see that the epsilon which performed best seems to be 0.5. So we use this kind of value in a real quantum computer using the machine of IBM Casablanca with an input of 30 values. We train the network with the first 23 values, and then we perform the testing as we show here on the last 7 data. We can see that the results from the reservoir follows quite closely the one expected theoretically. So finally, our last part of investigation regards the memory of the reservoir. So particularly we want to understand how this memory is affected by the epsilon parameter and the number of qubits of the reservoir. In order to understand this, we use the memory capacity matrix, which basically measure how the reservoir is able to recreate as output the input array sample at the time tau before. So basically we first compute the correlation between the output of the reservoir and the input evaluated at the time tau before for fixed tau. Then we sum over different values of tau to obtain the memory capacity. The results are here in the two plots. In the first plot, we see that the correlation decreases as expected as the tau increases. And the interesting part is that for increases epsilon, the correlation decreases more rapidly. And moreover, for epsilon fixed, it decreases less rapidly with the reservoir with a larger number of qubits. These observations are finally confirmed also in the last plot where we show the memory capacity, and again the total capacity decreases as the epsilon increases, whereas for fixed epsilon we can see that the increases as the number of qubits of the reservoir increases, and this increasement we measure is a linear increment, and is in accord with the previous results obtained with different kind of reservoir in the literature. With this, I conclude, and thank you.
Okay, thank you, Riccardo, very much for the presentation. The floor is open now for questions.
Sorry, this is probably a very naive question. I was trying to follow your talk, but I couldn't figure out what exactly you're trying to learn, basically.
A map, a dynamical, not a function, but a dynamical map. So, yeah. Like you have a dynamical map, you trying to learn the output for unseen input state.
Right, so to my understanding then you have a system and you have some outside environment and you're trying to learn how the environment moves such that you get the final result. Is that?
No, you don't. And what do you mean by environment?
The other spins in your system.
No, I mean you have an input, okay? You have some map that transforms that input in an output. You are trying to learn this kind of transformation. I mean, you learn, and then when you get a new input, it will predict the output as it was, as if it is the map.
Okay.
I mean, I don't know if...
and you're trying to do this using like these spins, right? These qubits. That's
yes.
Yeah.
Yes.
Thanks.
I mean, there is a reservoir which is made by qubits.
Yes. Yeah. Another question. So this map that you get, you made a comment that in one case it was linear and in the other case it was non-linear.
It's always. I mean, you can also emulate a linear map, but that's easier. That's a linear regression for that. The hardest thing is to emulate a non-linear map.
Okay, thanks.
Do you have any indication that this is might be better than a classical method for doing this?
We not have an indication, but what do we have is that the study on memory capacity of a reservoir of 5 qubits, not on gate model, but was on an NMR machine, is comparable with an ecosystem network of 500 nodes. So like the short memory capacity. So this is all the comparison we have.
So you said 5 qubits, did you say?
I don't remember exactly. 7 qubits is comparable to 500 nodes. I don't remember if it's 5 or 7 cube. It was published in an article, meaning you can get it.
So I guess the number of parameters in your state is comparable to the number of weights in the or the number of neurons in the neural network, is that right? I mean,
The number of what?
the number of parameters, if you have 7 qubits, right, you know, you
No,
have,
the-
128 parameters in the state, right?
There is also memory capacity.
Yeah,
As performance are comparable.
I see.
Any other question? And I have one. The interactions between the units are set randomly in the beginning?
The interaction between the qubits?
Yeah,
You mean?
to form the reservoir.
No, we start with a reservoir with all spin-up state. Okay, then we evolve with the map I showed you before. And evolving, it means applying gates also to qubit space. And
The spins are all up, like the interactions between the coupling between.
the coupling is if we apply with a U0 operator, you see there are a lot of CNOS, so we couple some qubits. I don't know if...
And those couplings are fixed?
Yes, I mean the operator U0 and U1 are fixed.
Okay. Very good. If there are no more questions, we thank Riccardo again.